Okay, so if I have a sample and I tell you that it's 1.6 molar, that means that there are 1.6 moles of barium chloride in every 1 liter of solution. So obviously if I said I have a half a liter, then that would be 0.8 moles. If I said I had 1 liter, then it would be 1.6, right? If I said I had a half a liter, then it would be 0.8. So you can take this any way you need to. You're going to multiply the volume in liters times the molarity to get how many moles there are. That's what makes it useful to then go on and use later on. So you take the number of liters, you multiply it by molarity. So those liters cancel out, and that would give you moles, because remember, every time we do something, we have to first get to moles to be able to do stoichiometry problems with it, which is kind of the essence of chemistry, right? It's that we're manipulating these chemical equations. So if I had something a little more complicated, like I said, I have 354 milliliters, then all I would need to do is convert that to liters first, dividing it by 1,000, so 0.354, and then I just multiply it by the 1.6. So that would tell me an easy way to get the number of moles. So this is kind of the standard form that we used in Chapter 5 to incorporate solutions into stoichiometry problems. So I'm assuming you're good up to this point, and I could give you, barring a complicated limiting reactant problem, I could give you any kind of molarity question and say, using the balanced equation, tell me what volume of the other reactant is required, stuff like that. So that's kind of where I'm assuming that you're at. If you are not comfortable with that stuff, please review Chapter 5. A good way to do that is doing the sample problems that are in the back of the chapter, but do the ones that have the answers so you can check yourself. You can also do the final exam practice questions. Well, they're practice now. Well, I guess they were then. Anyway, they're in the Pearson again. It's from Chem 1, but just do the Chapter 5 ones. Okay, so that's another option. Okay, so we kind of already reviewed some terminology, solute and solvent. And then we need a good reminder that solutions are a type of mixture. So literally at the very beginning of Chem 1, we talked about how we classify matter. So is it a compound? Is it an element? Is it a mixture of different compounds or elements? Is it a molecule versus an ionic compound? So a homogeneous mixture, that's synonymous with solution. Those are two terms that we didn't know the term solution yet when we talked about homogeneous mixtures, but that's what a homogeneous mixture is. It is a solution. We mix two things. They mix uniformly so that it looks like one substance. So I don't know what color barium chloride is. I think it might be yellow, but it's lead chloride. It's probably just clear. So I'll use copper sulfate for an example. Okay, so copper sulfate is like kind of a turquoisey color. So if you have water and copper sulfate and you mix them together, when you mix them, they do look different than when you started. It just doesn't just look like water anymore, but it looks uniform. It's like a clear solution. There's no undissolved particles in there. The copper breaks up into copper ions, and sulfate breaks into its ions, and then the water surrounds these molecules. So I have another picture of this later on, but I think I'll just draw it for us here. So then you get the water molecules, and now, since we've done intermolecular forces, you guys should be very clear on the fact that the water molecules would surround this ion with their hydrogens pointing in, and the water molecules would surround this ion with the oxygen pointing in. Okay, it's trying to maximize those positive, negative interactions. And this is why it looks uniform, is because it is trying to form the two things mixing together are forming new interactions Now, this would be an ion-dipole interaction, which is actually stronger than a standard hydrogen bonding intermolecular force, but it is similar to that in that it is a force between positives and negatives holding it together. And that's why it appears uniform, is because the solute completely breaks up, gets incorporated into the water, and so there is no real difference between any one segment because it's all just a bunch of water surrounding a sulfate and a copper and a sulfate and a copper throughout the whole solution. So the key point when we talk about things being homogeneous is that there are actual interactions forming. Now, we'll talk about these as like intermolecular forces, and most of them are intermolecular forces, but we also have ions interacting. It's like you're having a dipole-dipole force. No, I don't want to go into that much detail. We'll talk about that later. There are interactions that are either intermolecular forces or similar to intermolecular forces. They're positive and negative parts of the molecules or atoms that are attracting to each other. So that's what keeps them uniform. If you were to try and dissolve, that's a bad example. If you were to try to dissolve like sand into water, okay? Yeah, there are contaminants in sand, but the vast majority of it is silicon dioxide. So you shake it up, and you guys know that you can, like, if you don't put a ton of it in, you can probably get it to like kind of float in the water. That's not homogeneous though, because if you let it sit there, it's going to settle out and it's going to be two distinct things. The solute never dissolves into that solvent. Okay, let's just talk about a couple examples of different solutions. We are primarily going to just be dealing with the liquid ones in this chapter. Gases, though, can form solutions. Like, we don't normally think of it as a solution. We think of it as a mixture. But anytime you put gases together and you allow them to mix, as long as they don't react chemically, then you will have a homogeneous mixture. So in the air right now, there's nitrogen and carbon dioxide and water and oxygen and argon. Like, those are all mixed in the air, and it is a homogeneous mixture. Solids is something that we actually use a lot, but maybe we're not super like familiar with it. Is if you take two metals, you have to first melt them to get them to mix. So you kind of loosen up those bonds or interactions between the metal atoms. You mix them together and allow them to form new interactions with like neighboring metal atoms. So now instead of just having copper atoms interacting with their own copper atoms and zinc with itself, you start to get copper-zinc interactions, and they actually will line up so that they are pretty much just staggered, copper-zinc, 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 assuming you have equal amounts. And then they re-solidify, and then you have what's actually really a homogeneous mixture. That's what an alloy is. We're going to focus in on the liquid ones, though. So most common, we've talked about solids into a liquid, so salt into water or sugar into water. We can do liquid ones, though, like alcohol mixed into water. You could try to mix a liquid oil into water. It's not going to mix, right? It won't form a homogeneous solution or a homogeneous mixture. It'll just separate out. And then finally, we'll talk about gases and liquids. These are a little bit harder because you have to be closing the system off. So gases always have a tendency to mix in with other gases because they have enough kinetic energy to move away. So if you want to mix a gas into a liquid, you have to put a cap on it, and then only a certain number of gas molecules will stay in the gas phase, and the rest will stay in that liquid phase. So soda is the example here. Once you take that cap off, though, and let it sit there for a while, eventually all of that CO2 is going to escape. Okay, so what we're going to talk about today is the energy involved in how these solutions form. So we talked about energy in chapter 7. Then we talked about intermolecular forces in chapter 12. And now we're going to pull those two ideas together to talk about what intermolecular forces have to be broken and then what ones form when a solution is created and what is the energy associated with that. And that's going to tell us a lot about whether or not it will actually mix and become a solution. Terminology, don't forget soluble means it will dissolve or mix together. And insoluble means it won't. It'll just say separate. So if we say something is insoluble, it is not a homogeneous mixture. It's not even really, I guess if you shake up the oil and water, you can get it to mix temporarily. Okay, so in my first class, I didn't give this kind of preview idea, and I think that it was stressful for them. So we're going to talk very deep concept level about the energy today. But I want to reassure you that by the very end of today, beginning of Friday, we're going to simplify these energy concepts into a very simple way to know if two things will mix together. And that is what you guys read about in the chapter and in the videos, like dissolves like. It means if you've got two polar things, they'll probably dissolve and form a solution. If you have two nonpolar things, they'll probably dissolve and form a solution. If you have something that's polar and something that's nonpolar, though, they probably will not mix and form a solution. So like dissolves like, meaning if they have similar polarities, they will dissolve into each other. We are going to give an energy explanation today for why that happens. So this part is important. You're not going to use it, though, every time you decide, is something going to dissolve? Okay, that's the reassuring part. You're not going to have to look at energy and draw an energy diagram every single time. Okay, so this deciding whether something is going to be soluble or insoluble has a ton to do with the intermolecular forces in each, the solute and the solvent, how much energy it takes to break them apart, and how much energy is released when they come together. So picture that, I'll go to the actual nice picture. This one. Okay, so think of this as sodium chloride. So positive sodium, negative chlorine, and the water. So this is after they've mixed together, and there are some interactions that have now formed between the water molecules and each of the ions, okay? So we're going to talk about the process of dissolving salt into water as 3 distinct steps. It doesn't happen like this. When you stick a crystal of salt into water, it's going to simultaneously pull an ion off of that crystal and start to surround it with the water molecules, and another little ion's going to get pulled off and get surrounded, and it kind of happens all simultaneously that these individual ions get pulled off of the solute and surrounded by the water. We're going to pretend like it's 3 distinct steps, though, and that's what this picture up here is going to show us, okay? So the first step, which is right here in the picture, is going to be breaking apart the solute particles. So in the case of sodium chloride, this would be taking salt and breaking it into sodium and chlorine. This is a side note. It's always nice, though, if you guys have seen this before you go to organic chemistry. So this is ethanol. 2 carbons, 3 hydrogens, oxygen, hydrogen on the end. In organic chemistry, the way you draw this is like that. So on an end or a point, you know that that's a carbon. If it's connected to another atom, then there's not a carbon at the end. So this would be a carbon, and you know it has 3 hydrogens because carbon always has to have 4 bonds. So there's 3 hydrogens there. Up on that carbon, you've already got 2 bonds, so it has 2 hydrogens. So like the hydrogens are implied, you don't write them in. I'm showing you this not because you have to know it for me, but because I'm going to draw alcohol like that right now. So if I have ethanol, which is not an ionic compound, breaking apart the solute, I would start with ethanol, lots of little ethanol molecules. Oh, that was, there we go. Something like this, okay? And these would have a bunch of little interactions between the negatives and the positives of the different ethanol molecules, okay? So if I was breaking apart that solute, they would still be ethanol. They would just all be separated from each other. I would just break apart those intermolecular forces and have them all separated. So it kind of depends on what type of molecule you're talking about. If it's a molecule, you're breaking intermolecular forces. It's still staying as a molecule. It's still water or ethanol or sugar. They're just not attached to each other anymore. It's almost like you're boiling them, but you're not really. Because this happens all 3 of these steps is going to happen together. Okay, so that's step 1, breaking apart the solute particles. They try to show you this by showing the solute here is all structured and ordered, and then up here, they're split apart from each other. Okay, there is a certain amount of energy associated with this, and we call it the delta H of the solute. So the solute, because it's breaking apart the solute particles. The second step here is breaking apart the solvent particles. So it's energy associated with that is called the delta H of solvent. Why do we have to break apart the solvent? Because aren't we just putting something into the solvent? Well, think about you've got all of this water interacting with itself. So there's all these interactions. I'll go ahead and draw it. There's all these interactions between water molecules. Okay, positive sides connected to negative sides, and throughout a container of pure water, there's all of these water interactions. Well, if I want to stick a sodium ion into water, like I did in this picture below, if I want to put that sodium in there, I'm going to first have to break apart the water from itself so that there's somewhere for the sodium to go. We often talk about it like creating holes in the solvent. So you're creating a spot for that solute to go into. So in the case of water, that would mean breaking apart hydrogen bonds in order to allow, so it's still water, it's just water all separated from each other to allow the sodium to fit into one of those little spots. It's not all the water, because a solvent, there's lots more solvent than there is solute, but there's some gaps or holes that need to be formed. So holes in the solvent is what we're talking about, little spots for those salt ions to go. Okay, so solvent has to be broken apart as well. Okay, so now we've broken apart the solvent, we've broken apart the solute, that's what's up at the top. Solvent separated, solute separated, and then they come together and mix. Okay, and we get the solution. So the energy associated with that is called the delta H of mixing. So in the case of sodium and water, this would be where the interaction between the sodium and the water gets formed. You guys should be really clear now why the oxygen is the thing surrounding the sodium ions. Okay, so it's these little interactions now that we're talking about being formed. Solute and solvent particles, attractions are formed. Okay, take 1 minute, and I want you to tell me, write on your paper, whatever, talk to your neighbor about it, what the sign, positive or negative, of each step's delta H should be. So like, is the delta H of the solute positive or negative? Is the delta H solvent positive or negative? Is the delta H of mixing positive or negative? You can look at the picture, you can look at the words for hints, talk to your neighbor through it, about it. Yeah.
For number 3, is it delta H solution or delta H mixing?
So this is delta H mixing. The delta H of solution is going to be combining all 3 of them, or like the difference of where you start and where you finish.
Okay.
And I'll clarify that again in a second. So we're just talking about these 3 right now. Not like highlighting them is going to help since I have so much other stuff up there. Okay, so steps 1 and 2, positive. Well, I just gave it away. Steps 1 and 2 are the same. Are they positive or negative? Positive. Why?
Energy is going in
And why does it have to be going in?
because you need it to break bonds.
Exactly. You're breaking an attraction there. Anytime you're breaking apart 2 things that want to be together, it's going to take energy. So steps 1 and 2 are going to be positive because these are breaking. Also, it's showing us in the picture. You have to go up in energy, up in energy. Okay? So every single time, those first 2 steps are going to be positive. Step 3, we're forming, so it should be negative. That's right. Okay? Energy is released when 2 things that are attracted to each other interact. So delta H of mixing will always be negative. So the question is, how big are these positives versus how big is that negative? Okay? The way this one is drawn, obviously the negative is much larger. And I think this is actually the next page. So if you want to skip forward to where you're writing the notes. Which side, energy released or energy required, is larger? Well, just from the size of the arrow, we can see that the energy released is larger. I could give these numbers and say, like, maybe this is 50 kilojoules. These look about the same, so I'll call this 50 kilojoules. And this one I'll say is like 120, negative 120. Okay? So the release, the delta H of mixing is larger. What does this mean about the sign of delta H solution? So the change overall, like this is initial, and this is final. So going from here to there, we're going to call that the delta H of the solution. It's really just the sum of all of the energy in these 3 steps. So 2 that are required, 1 that's negative and released. The difference between those is going to be the delta H of the solution. So in this instance, that would just be negative 20 kilojoules. There would be 20 kilojoules of heat released in this process. So whatever this solute solvent is, when we mix them together, it's going to feel hot. There's going to be energy coming off.
You said it was the sum of all three?
Yeah, so when you, and then I said something like difference, didn't I? The difference between the two. So you already incorporate the negative sign. So on the next slide, we're going to give you actual values here. So if you didn't have the negative there, you would have to take the one that's releasing and subtract the ones that are being required. But we give you that by adding the negative in there.
Okay.
So you just add them together. Just accounting for the negative, actually including the negative in your sum. It's funny, whenever you start thinking of math from like you don't just do it and you think about why you're doing it and why we use the words we do, it makes so much more sense why, like what negatives mean. I have a hard time explaining it to my kids because you're like, how can you have negative something? Well, you don't, it's just a different direction. Okay, so what does this mean about the sign? We just gave it fake numbers, but if the energy that's being released is more than the energy that's required for those two steps, it's going to be negative. There's going to be an overall release in energy. Overall release in energy. And let me just reiterate this. We're saying this one is bigger than these two together. Yep.
So does this apply, so it can either be released or required depending on which reaction it is, or is it always going to be exothermic?
Yes, this is a great question. So is this always going to be exothermic? The bottom question here says, is this favorable? Like, is this sign of delta H favorable? Usually we think of an exothermic reaction as more likely. Like, this would be considered a favorable interaction because it's decreasing in potential energy. So like if we were just to draw an energy diagram, not worrying about the steps, just worrying about where we started and where we finished, it would go down in energy. And the question was, can it be the other way? Can we have it going up in energy? Each step in the process is always positive or negative, right? Like these two are always positive. This is always negative. The overall is really going to just depend on the difference between those. So let's draw. I'm going to do it on this one, even though these numbers are not in corresponding with this. So I'll do it on the side and then we'll come do this one, okay? So we could have something that took a certain amount of energy to break apart the solute, took a certain amount of energy to break apart the solvent, but for some reason, I'm gonna draw that a little bit more, didn't release quite as much energy. So this would have a delta H of solution that would be positive, because we're most concerned about this little chunk here. The way we find this is by comparing energy required to energy released. But this little chunk here is what tells us the overall energy change. And in this instance, it would be positive, which means we'd be putting energy in. It would be increasing in potential energy. That is very hard for us to conceptualize because that would be like the pencil coming off of the table on its own. Like, I don't have to put energy, well, this says energy in. It would have to get energy from somewhere, but it would be going up in potential energy, and the second I let it go, it would just go back down, right? This is not favorable, but it can happen. So I'm going to say unfavorable. Now, I'm going to tell you the rest of the story, or at least part of the rest of the story, and they do talk about this in this section. I think it's in section 3. You don't have to know this, and that's why it's not in the notes, but it's helpful a lot of times for people to feel comfortable with why is this able to happen, because like the pencil is just going to fall back down, right? Why does this happen? Why does the mixture stay together? Okay, so any process in the universe has two factors that dictate whether it's going to occur. The first is the change in potential energy, which is what we're really talking about right here. And the second is a property called entropy. Totally a crapshoot whether you've heard about this or not. Some people talk about it very briefly in high school, chemistry or physics. You may have heard about it in biology. We usually will describe it as the tendency for things to go to disorder. So if you don't put any energy in, your room's gonna get messy, right? Like it's much easier to drop your sock on the floor or drop it over here or drop it over here than to get it in the laundry basket. Okay, so these two things and the balance between these two things is what decides whether anything will happen in the universe. Gravity, entropy is always unfavorable, so we always have to rely on potential energy to dictate whether or not something's gonna fall, okay? With dissolving things, the entropy is always favorable, which means the potential energy could be favorable or it could be slightly unfavorable and still occur. Because entropy and potential energy are also like a balance thing. As long as this one isn't too unfavorable, it can be outweighed by entropy. Again, you don't actually have to know this. It's just a helpful thing for you to understand so that you can be okay with the fact that an endothermic reaction can happen, which shouldn't be that bothersome. We did lots of reactions, chemical reactions, where the delta H was positive. So that's okay. There are plenty of things in the universe where this happens. The reason why they're able to happen is because of the entropy. Okay, so this is one example of where it would be positive. What time is it, 40? I'm just gonna do this one together with us. So we're gonna draw, yes, no? Okay, let's do the quantity together and then I'll let you draw the energy diagram by yourself for a second. Okay, so looking at this particular example, it actually gives us numbers associated with the different steps. So the energy that's going to be required in both of the first two steps is 39.3 kilojoules. But there's an overall release of energy from step 3, and that's equivalent to negative 91.7. So as long as we, include the negative here, we would just add 39.3 plus negative 91.7. It is kind of like we're subtracting, but we're just doing it by adding a negative. Those are the same thing. Okay, so that means that the overall change in enthalpy is exothermic. So that is favorable. And it's 52.4 kilojoules favorable. So if we were to sketch out an energy diagram for this, step 1 would take a little bit of energy, 16.5. Step 2 would take a little bit more. But step 3 would release more than half, or more than twice as much as was required. Okay, the purple one, the very exothermic one, the fact that releases so much energy will tell us that this process will occur and that solute will be soluble in that solvent, okay? It will dissolve. So if a solute-solvent interaction is exothermic, even if it's only slightly exothermic, it will occur. If it's slightly endothermic, even though that's unfavorable, it will also occur. Now, slightly is a, not a very specific term, right? We're just going to keep it general, though, right now. So if it's slightly endothermic, it will also dissolve. But the more endothermic it gets, the less and less likely it is for it to happen. So that is probably not going to happen, okay? The more endothermic it is, the less likely it is to occur. So on the far end, we have something exothermic, that's going to happen. The more we creep towards them being equivalent, still going to happen. Once we start to get the release being not compensating fully for all the energy that was required, that's when we start to be like, oh, we're not quite sure whether it's going to happen. It depends on how big that difference is. And thankfully, you won't have to do anything to decide how big is big. You just need to understand the general concept here, kind of how we model this. Okay, so what I just said about like exothermic, slightly equivalent, slightly endothermic, that's summarized here in this table. Are you okay, Maggie? That's hilarious. I'm sure it was funny. I was kind of like, did you guys notice in the test when like the table got shoved like dramatically? Wasn't that during the exam? Yeah, it was pretty great. Okay, so this idea of comparing the energies is summarized here. So don't forget, this is step 1. Energy is released. This is step 2, where energy is absorbed. So what they're saying here is if this one is really big, a big negative compared to this one, the solution's going to form. If they're about equivalent, the solution's also going to form. Even if it's like, and I'm going to say about here, because even if it's slightly higher on the energy required side, it's still going to form. But if you start to get this being significantly higher, the energy required versus the energy that's released, I wish they had flip-flopped this table so that it stayed consistent with how the pictures are drawn, but whatever. I should remake it my own. Then it really is going to depend on how big of a difference it is. Okay, so this one we don't really know. Okay, now the last thing is we need to talk about what dictates the size of these. How do we know how big these arrows are? How much energy is required versus how much energy is released? How can we get a sense of that? And that all has to do with the intermolecular forces. Okay, so I love this because this basically summarizes all 3 steps. This is step 1, breaking apart those interactions. So if you've got sodium chloride, those are ionic bonds. Those are really strong. So in that instance, your number 1 is going to take a lot of energy. Step 2, breaking apart the solvent. Let's pretend that's water. That's also going to take a lot of energy to break apart those water molecules because there's hydrogen bonding, right? So why in the world does salt dissolve in water if you have to put a ton of energy in to break apart the ions, ton of energy in to break apart the water? Because this ion dipole interaction is really, really big as far as the energy that's released. So it's okay if the first 2 steps take a lot of energy, as long as the third one releases enough to compensate. So you guys already know about steps 1 and 2 because you've done all the intermolecular force stuff. The only thing we need to talk about is how do we decide the size of those forces between solute and solvent. And it's the same exact thing. It's just now you're comparing between 2 different molecules. Okay, so this is the ion dipole one. right? This is going to be the strongest of all of them, even stronger than two hydrogen bonding things. And then at the far end, the weak interaction, so these would be small amounts of energy released, would be two things that are nonpolar. So it's the same thing as last chapter. Look at it and decide, is it nonpolar or polar? If it's nonpolar, they're just dispersion forces. They're very weak, okay? So little bit of energy released. If they're polar, they're dipole forces. More energy released. If it's hydrogen bonding, even more is released. And if it's ion dipole, even more is going to be released. Now, what about if we try to take something like, let's use pentane. And I'm going to use the next page, but I'm not going to use the box that's on there, so just ignore that. I'm going to take pentane and water, and I'm going to see what happens when those guys interact, okay? Because when I look at the interaction of pentane and water, can they form hydrogen bonding? Like, water has the capacity to form hydrogen bonding, but pentane doesn't. So when you have two molecules that are from two different groups, the one that's the weakest defines everything. The pentane interacting with water can only really form dispersion forces because the pentane is only capable of dispersion forces. Now, the pentane water might be a little bit stronger than pentane with itself, but not enough to really consider. So whatever thing has the weaker force, that's what dictates the size of this energy release. So we're going to draw a picture for water and pentane, so ignore this. So if I wanted to try to mix water and pentane, that's supposed to be a 5, okay? Step 1, breaking apart the pentane. This is going to be my solute, by the way. Okay, so pentane is carbon hydrogen, it's nonpolar, it's dispersion forces, so they're pretty weak. So breaking apart shouldn't take a whole lot of energy. Water, however, is hydrogen bonding, takes a ton of energy to break those apart, okay? Now, the interaction between water and pentane is very weak because pentane is only capable of dispersion forces. So step 3 is going to be quite small. So now we're talking about a large endothermic delta H of solution. So this is why like dissolves like, and things that are unlike will not dissolve. When you get something that's polar, and even more so than just polar, I'm going to say very polar, because that's what hydrogen bonding is, and something that's non-polar, they will not mix because the energy that's released when they interact is very small compared to the energy required to break them apart. So this is the energy explanation for why like dissolves like, or in this example, like does not dissolve like. Okay? The energy is not enough to compensate for all that energy that was required. That was fun. Okay, so we will pick up here on Friday, and then we'll basically be halfway through 14 at spring break. So what I'm going to do, just so you're aware, one of my kids is having a surgery during spring break, and it got pushed till Friday. So I probably am not going to have class on Monday, just as a heads up. So we will probably just do a video, but I've structured it so that I think it's mostly mathy stuff. So anyway, just keep an eye on your email to know for sure. I did not mean to disconnect that already. This Friday?
Yes.
Oh, okay. I'll just record it. Okay. All right. Just make sure to check like mid-afternoon. It'll be on there.